Hello, everyone. So I want to jump right back where we ended yesterday to remind you we were looking for just general description of vibration of a string. And in particular, we are interested in the standing waves on a string, which can only take on certain specific forms, right? So from your introductory class, you know that uh, the only way in which a string can vibrate in a pattern of in a standing wave pattern is if it vibrates in the first mode or the second mode or third mode and so on, because that's the only pattern of vibration that respects the boundary conditions. So we're interested in these very, very special solutions called modes, or they're also called normal modes, but the word normal doesn't have any meaning to you right now. So I just called them modes. And I noted that, well, any general vibration can be expressed as an appropriate sum of these modes. If you tune in coefficients and phases, then you can express everything in terms of these modes. So the modes are very important. So to seek these modes, we started sort of from scratch with a general equation that a deflection of a string obeys. I'm not sure if I don't remember if I said that. I think I didn't. This is called a wave equation. Many simple waves obey this equation. So for example, not just the motion of a string, not just the string, but also, for example, the density of air, right? So when I speak, I create disturbance in the air, and the density of air obeys this equation, right? So sound waves basically obey this equation, unless it's they are extremely loud sound waves. A lot of simple things, simple elastic materials, drum heads, strings, simple media like air, they all obey this equation. So that's an equation of motion, an equation obeyed by some kind of an elastic medium. Y is, in the case of a string, is a displacement, a vertical displacement of a string. X is the coordinate, T is time. And in addition to the equation, we also have boundary conditions. If the string is fixed at both ends, then the boundary condition is that the Y, or the displacement of the vertical displacement of the string, must be 0 at those ends, which we call X equals 0 and X equals L. And now, because we're seeking modal solutions, what are those modal solutions? They're solutions in which every point on the string experiences the same dynamics as every other point. And that means that the temporal part of the solution must be separate from the spatial part. In other words, we're interested in a solution in which the two variables separate, in which the in which the actual function for the displacement of a string at point x time t separates into a product of some function of time and some function of space, which I call tau and big Y. Right. So this is the form of the solution that we're seeking. If we're seeking modes, we're seeking this kind of solution. And then the rest was to just plug it in. Okay, so we plug this variable separable. This is called separation of variables. This procedure is called separation of variables. And we plug this variable separable form into the equation of motion, the wave equation, and then we just do algebra. And I think I may have left off last time when I did it. I think at the last step, what I did is I took the derivatives, that I divided the whole solution by y times tau, and on the left-hand side, I got the second derivative of tau with respect to time divided by tau itself. On the right-hand side, it should be v squared times the second derivative of y with respect to space divided by the y itself. So I think I left this off last time. Today, when I was going over that, I realized that that was left off. But the point is this, that now we end up with something that's only function of time on the left-hand side, only function of space on the right-hand side. And the only way that that can be, the only way that a function of time equals a function of space, is if both are a constant. Constant is a function here, right here, C. And so that's where we left, right? So let me rewrite this. We have d squared tau dt squared equals c tau, and d squared y with respect to x squared equals c over v squared y. This is where we are. So the first thing I'm going to do is, this will seem like odd, random. I'm just going to call the c. This c is called the separation constant, right? So c it's constant because it is a constant, and separation because it separates. Having a lot of technology difficulties today, folks. I was recording for 1 hour until I realized I wasn't actually recording. I thought I was recording, so I lost a whole hour of time. So you can see that, you know, left-hand side equals right-hand side, and both must be equal to c. So it's a separation constant. That's why it's called a separation constant. And so now what I'm going to do is I'm going to, yeah, and this procedure is called separation of variables. Okay. Now, what I'm going to do is I'm going to do that, something that looks completely out of the blue. Let me just change the name. Let me call C. I don't have to, but this is going to be a little bit more elegant if I do this. I'm going to call it minus omega squared. This is suggestive. It's suggestive. It's in foresight that, first of all, that it's going to be a negative thing. And moreover, that the meaning of C is it's minus the square of the angular frequency. So this is in foresight. In general, I don't have to do this, right? So if I am a master of this technique, I don't have to do this. But for teaching, I'm going to do this. Okay? And so then what we have is we have d squared tau dt squared equals minus omega squared tau, and d squared y dx squared equals minus omega squared over v squared times the y. So this is equation 1, and this is equation 2. Okay, so equation 2 has two solutions. Sine of omega over v x and cosine of omega over v times x. And you can see for yourself that, just plug it in and see, convince yourself that that's indeed the case. So a general solution is y of x equals some coefficient, some constant sine omega over v x, okay, plus some other coefficient times cosine of omega over v times x. And what I just did is I basically wrote down a general solution to an ordinary differential equation, something that you should be comfortable with from your linear analysis class. Now, of course, there are lots of differential equations out there. Some are very difficult to solve, but this one you must have seen before. And I just wrote down that general solution. Okay, good. So I have a general solution. Now we have to do something that's extremely important. Actually, before that, let's realize that omega over v equals the wave number k. And so therefore omega equals k times v. So it's a relationship that connects angular frequency and the wave number. We've already seen something like that. So this is called the dispersion relation. So now let's do something that's very important. Apply boundary conditions. Okay, so we've solved as much as we can the spatial differential equation. Now we need to apply boundary conditions. So there are two. First is that the displacement at x equals 0 is 0 for all times. That means big Y at x equals 0 has to be 0. Okay, so 0 equals a sine of 0. Well, that's automatically 0 plus b cosine of 0. Cosine of 0 is 1. So this tells us that b equals 0. Boom. So we kind of knock out this part of the solution. The second boundary condition is that the displacement of the string at x equals L must be 0 for all times. That means the big Y, big Y at x equals L has to be 0. Here's the big Y. The b is already 0. And so therefore, we have 0 equals a times the sine of KL equals 0. So there are two ways that this can happen. Either a equals 0, then that means that y equals 0. It's true, but it's not an interesting solution. Y equals 0 is always a solution to the wave equation. We're not interested in that, okay? So this is called a trivial solution. It's not interesting. Or sine of KL equals 0. And that means that k's can only take on discrete values. So KL equals n pi, where n is either 0, well, that's again not an interesting solution, or it can be plus or minus 1, plus or minus 2, and so on. Okay. All right, so then k equals n pi over L. By the way, the minus, the negative k's, they're not interesting also because that's just equivalent to flipping the mode upside down. That will automatically be included in the full solution. So we only need positive n's. And so we see that there is an infinite set of discrete modes. Okay, each mode has a single shape. We have sorry, y sub n of x equals a sub n sine of kn x, where kn equals n pi over L. And by the way, the wavelength, what's the wavelength? Well, we have 2 pi over k sub n equals lambda sub n. So that's n pi over L. So therefore, lambda sub n equals 2L. Sorry, I'm writing something dumb. Okay, so this is lambda sub n And then let's just plug in our k sub n's, 2 pi over n pi times L equals lambda sub n. Okay, so lambda sub n equals 2L over n. So you have lambda 1 equals 2L, lambda 2 equals L, lambda 3 equals 2/3 L, and so on. Exactly as we've already seen just from basic visual analysis. Okay, so we learn two things automatically, that modes are sinusoidal, and in general that will not be the case, right? You can have other equations of motion that will produce waves that will produce, sorry, modes of other shapes. In this case, they happen to be sinusoidal, but in general, that's not the case. And I gave you an example with a kind of a very thin wire, or like a steel girder. Okay, good. So we learned about the shape of the modes. What about the temporal solution? Well, we have d squared tau dt squared equals minus omega sub n squared tau. Notice that omegas also have to be discrete because omega equals kv. So since k is discrete, you have a discrete ladder of solutions. Then the frequencies are also discrete, right? Okay, and so this is basically the same. It has the same kind of, it's basically the same equation. And so, yes, you can write the general solution again as some coefficient times the sine omega t plus another coefficient times the cosine of omega t, or you can combine them. It will be more convenient to combine them into a different form. So tau of t equals tau naught. Well, let me call it like this. Let me call it a cosine omega n t plus, so this is a sub n times phi sub n. Okay? And so altogether, the nth solution as a function of space and time is a sub n times sine knx times cosine. Let me pause. I'm going to write this a little bit neater. Okay. And you realize that this is a product of two coefficients, right? So I can just rewrite this simply, more simply. I can just say that this is y0, nth y0 times sine knx times cosine omega n t plus phi n. And again, k sub n equals n pi over L, and omega sub n equals v times k sub n. Okay, so this is it. This is like a general solution of a mode. And how do we visualize this? How do we visualize this? So this might look too intimidating for you. Okay, so if I drop the sub n, okay, so to see what this means, let me lighten the notation. What does the sub n mean? It means you have a discrete ladder of states, and each is labeled by index n, 1, 2, 3, and so on. But the essence of what we have is we have the function of space and time, is some initial deflection times the spatial part times the temporal part. And so you've seen this in your math before, right? So at t equals 0, okay, you have some sort of a sinusoidal deflection. So this is at t so sort of t equals 0, right? So this is x, right? And this is the deflection. Here, let's do it like that, right? At a later time, as time evolves, well, this thing is left alone. The spatial pattern is left alone, but this factor varies sinusoidally, right? So you might have some kind of a different deflection, and then different deflection, and then this, and then this, and then this, and then go back to this, and so on. So it's a wave. It's the mode breathing, the whole mode oscillates. So this is n equals 1. And what about n equals 2? Well, n equals 2, right? This is L. So n equals 2 is like this, that, 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 like that, like that, and then it comes back, right? So it oscillates like that. And you have a node here. Sorry for the bad drawing. So this is called node, and this is called the antinode. This is also called the antinode right here. So the shape of the mode stays the same as advertised, but you can think of this as a time-dependent amplitude. Okay, so time-dependent amplitude. So there will be a moment in time when the whole thing is just collapsed, and then it will breathe again, and then it collapses and breathes again. So that's what it is. So that's the visualization of what this mode represents. And I suppress the index n just to make it a little bit less intimidating for you. But for each mode, you have each mode's maximal amplitude, each mode's wave number, each mode's frequency, and each mode's phase constant. Okay? And so now what remains is to put all these modes together. Okay? We can add up these modes, we can add them together. And we will talk about that some other time. But we have found a discrete ladder, a discrete set of modes, right? Each mode has its own wave number, or its own wavelength. Each mode has its own frequency. So for example, the angular frequency of this is V times what is it? K sub n is n pi over L. So this is pi over L, and angular frequency of 2 is twice that, 2V and 2V pi over L. You can sort of probably guess where this is going. In quantum mechanics, wave number can quantify momentum, and frequency quantifies energy. And you can see that here we have a discrete ladder of solutions with a discrete set of frequencies. So when we do something similar in quantum mechanical problems, in particular, solution to the problem of a particle in a rigid box will be very similar to this. We'll basically go through this again. Okay. The frequencies will acquire a new meaning, and they will be proportional to energies, and automatically out comes the energy quantization, the discretization of energy. So the quantization or discretization of solutions is not really a quantum thing. It existed in the 19th century, for example, for waves on a string. But that was applied to things like frequencies. And only when when people started realizing that particles behave as waves, it became clear that frequency, frequency has something to do with energy, and therefore there will be a quantization of energy. Okay. Okay. What we will do on Monday is I might have a few words to say about this. And after that, we will again switch gears a little bit, and we will talk about just motion, classical motion of particles, types of motion that can happen. You can have bounded motion, unbounded motion. And then we will quickly go over some general properties that a wave function must have. And then we'll start talking about, well, what do you do if you have interactions, right? We talked about motion of a free particle. I wrote down Schrödinger's equation for that special case, and a solution for that special case, the plane wave solution. What if the particle is experiencing a force? How do you find the wave function in that case? So that's really the subject of chapter 5 and chapter 6. And we will see that this procedure that we have just performed will be the same procedure that we will apply to find wave functions of particles when they are bounded. Okay, when they're unbound, it will be something else. But when they're bound, it will look very similar to what we just did for a wave on a string. Okay, so stay put, watch for announcements, and I will do a second video for today's lecture where I walk over some of the homework, right? I want to give you guidance on some of the homework problems. I'll see you then. Bye.